So our next presenter is Roger Schwenke, who has probably one of the coolest bios of any audio acoustical engineer I've ever known. He's a senior scientist at Myers Sound Lab. Roger holds a doctorate in acoustics from Penn State University and has appeared as an expert in acoustics several times on Discovery Channel's Mythbusters. You're actually an honorary Mythbuster, aren't you? So, excellent. Thank you. Welcome.
So thank you for having me, and thank you again for spending some time thinking about audio. Many test signals exist already and can be used for measuring the maximum SPL of a loudspeaker, but none of them has been universally recognized as representing what a loudspeaker will do for real content. So for instance, you could measure the maximum SPL of a loudspeaker just with a sine tone, and you would get a number, but that wouldn't necessarily tell you how loud is that speaker going to be for content that you actually want to listen to. And that's similarly true for other noises, as I'll show for a minute, in a minute. So we wanted to investigate that. And the title of this, the title of my presentation says a new signal, and it is new, but it's not brand new. So it's been released for about a year now. We've been using it internally before that, and we've done some demos at trade shows, etc. This is our first really formal presentation of the whole theory and background behind what we did. But like I said, so there was a Mix magazine had their event, Sound for Film, about a month ago, and so I did some demos there, and there was some interest in it. At the end of it, someone said, "Oh, okay, so this is when I'm working in a new room and I play Pink and I get 85 and everything seems fine, but then I play my mix and the loud part of the mix sounds terrible. So why is that? Did something change? Is there something wrong with the mix? Or is it the loudspeakers in this room just can't do what the loudspeakers in my last room did?" And that's it. That's what we're looking to do here. Our intention is not to replace what's done before. So that process, bringing up peak noise and getting 85 dB and getting the right frequency response, that can still happen as is. That's fine, that's valid, and that sets your sensitivity and your frequency response, but it doesn't tell you, can that system get to 105? It doesn't tell you if you can get to 95. It doesn't even tell you if you can get to 86. So that's what we're after, is we have, this sensitivity, a certain dBFS is supposed to produce a certain dB SPL. Well, it's pretty easy to calculate what SPL full scale digital should produce. So I have an analysis that I'll show in a bit. We suspected that it's not just the spectrum, it's just not the overall crest factor. There are signals with different spectra, there are signals with different crest factor. We thought it has something to do with the crest factor as a function of frequency. And so I'll show you that analysis, but now I'm going to show you a very simple demonstration to kick it off. So what if you just apply a low pass filter or a high pass filter? So here on the bottom in gray, we have a little graphic of a low pass filter at 1 kilohertz. Later on, it'll switch to a high pass filter, and we'll see what the peak and RMS level of these signals are. So what we're showing here, the very solid bar is your RMS level. The thin green line there is your most recent peak, and the next green line is the peak hold, the highest peak since the beginning. And the difference between those, the peak and the RMS, is what we often call crest factor, and here we're looking at the whole signal. We're going to show pink noise on the top and a selection of music at the bottom, and I'll get into the selection of content later on. So here we'll play this short little video, and you can see at low frequencies we have very similar peak and average levels between pink noise and music. But now if we switch to the high pass filter, pink noise is not that much different between peak and average levels, but music is dramatically different. And honestly, the music part I don't find too surprising. So in order to make an impulse, in order to have a high rise time, you have to have high frequencies. And so I found it pretty intuitive. Everyone I've talked to since has found it relatively intuitive that the crest factor of real signals is higher at higher frequencies. What was really surprising is that that's not true for pink noise. And that was the thing that most caught my attention. Is I expected the crest factor to go up with frequency like any other signal. Here we're looking at just the two, the lower half of what we can hear and the upper half of what we can hear. That's dramatic. You can do it in octave bands. It doesn't matter too much what you do to pink noise. It always ends up about 12 dB crest factor. And if you look at what AES2 has done in recent years, they also showed that you can try to crush down the crest factor of pink noise. You can try to make it even less. And the moment you pass it through any real system, it pops right back to 12 dB. So that's a really interesting property that pink noise has. And that's maybe useful in certain situations, but unfortunately, it doesn't represent what real content is like, and I'll show you that now. So what I'm showing now is an analysis of a very large number of songs. I'm not going to list every one of them. I'm going to tell you some categories here. So each one is from a different album and includes pitch singing, rapping, female vocals, male vocals, instrumental music, music with synthesized instruments, amplified instruments, acoustic instruments, music recorded live and in the studio, Eastern and Western classical music, dance, rap, rock, jazz, funk, in a variety of decades. I hope I haven't left any of you out, but the intention here was to be an impressively wide scope. And so those are the gray lines here that I'm plotting. And I'm also plotting pink noise. So pink noise, of course, has this sort of fairness approach. It has the same energy at all frequencies. But that's not what's going on with real content. And that's been recognized for a significant amount of time. And so there are other signals with names like simulated program material. What I'm plotting here is EIA 426B. So that's the red curve here. So the red curve is acknowledging that real program material, the RMS level, tends to roll off with frequency. And it does pretty nicely reflect what's happening in the data. And M noise, which is the signal I'm talking about and presenting about, we very similarly, we rule off the RMS level at high frequencies. But it's a different story for peak levels. So now watch very carefully the gray lines as I switch from RMS to peak. So here we are looking at the peak levels in octave bands for all that same content. And you'll see that, compare that to the red line. So the simulated program material was very much in the middle of all that data before for the RMS levels, and now the peak levels are all exceeding the simulated program material. Simulated program material is just filtered pink noise, and we know that filtering pink noise gets you about 12 dB no matter what you do, no matter what the bandwidth is, or if you previously tried to crush it down to a smaller crest factor or not. So simulated program material While the RMS levels were good, the peak levels aren't right. Now, on the other hand, pink noise is looking pretty good in this graph. So pink noise, since it has this constant crest factor, it has a constant RMS level with frequency, it also has a relatively constant peak level with frequency. And so the peak levels with pink noise do rather well reflect what actual content does. And so that was our approach with this new signal, M noise, was to have peak levels like pink noise, have peak levels that were relatively constant with frequency. Now I'll attempt to go back. But have RMS levels that reduce in the high frequencies. And you cannot do that by simply filtering the pink noise. You have to do something different. And that's what's new about this signal. Okay, so let's talk about crest factor. I keep talking about crest factor. Crest factor is just the difference between the peak and RMS. So of course we can also plot that. And here the gray lines are again all of those tracks that I talked about, the crest factor in octave bands, and they all increase. Without exception, they increase. They increase dramatically. The crest factor of real content increases dramatically with frequency, and most test signals do not. Pink noise does not. Simulated program material does not. Any filtered pink noise will have a constant crest factor as a function of frequency. So here we are talking about motion pictures and television. I've talked about music so far. Let's move on and talk about some of the other content that you'd expect to see in motion pictures and television. So in the world of speech, there's also a standard for the RMS spectra, ANSI S3.5. Specifies a standard RMS levels for speech, and that's plotted this here in red. And the gray lines here are now some other data that I've analyzed. So here I've included spoken numerals, reading instructions, reading a novel, interviews, a conversation at a table in a restaurant, in a busy restaurant, and background talking in an office. So those two examples, the restaurant and the office, there's other background noises in the recording. So there's HVAC and there's trucks driving by in the street outside and all that sort of thing. So you'll see some elevated RMS levels below 100 hertz in these graphs. That is those environmental recordings in the restaurant and the office. That's not speech. So this red curve here, ANSI's RMS levels are matching pretty well with this audio samples that I found. In particular, take a look at the RMS, the red curve there is pretty much right in the middle of all that data, right in the middle of all the gray lines. So now I'm going to switch to the peak levels. So these are the peak levels in speech. And now you see that that red line is below almost all of the data. So the ANSI speech noise, again, is filtered pink noise. It's always going to have a 12 dB crest factor as a function of frequency. That doesn't match what happens with real signals. So again, I'll plot the crest factor. So this is the crest factor as a function of frequency for all of those speech signals. And again, it rises dramatically with frequency. Again, this red curve is the ANSI 3.5 crest factor, not simulated program material, but it has the same crest factor again as pink noise because it's just filtered pink noise. So now here's what you're all waiting for, I'm sure, is cinema content. Cinema content, of course, is much longer. It takes a lot more time to analyze. And there's intellectual property that is an impediment to a very wide scale analysis. But we have the entirety of a very early surround sound movie in here, as well as a very recent movie known for being particularly loud. We have a number of clips of different movies that include speech and music and action, you know, a horse battle scene, all the kinds of things that you would think might be interesting in the audio of a movie. And so again, we see that the RMS levels go down at higher frequencies, and the peak levels not nearly as much. And the crest factor, again, without exception, rises with frequency dramatically more than our standard test signals. And so hopefully you haven't been listening to me during this slide. I'm just babbling. You're just looking at the trend here and how remarkably similar even though this is a small sample of cinema audio, we've seen a large sample of speech, we've seen a large sample of music. We have our intuition that crest factor increases with frequency, and every sample of actual content we look at, the crest factor, without exception, increases with frequency. Really, the only surprising thing here is that our test signals do not. That's really the most surprising thing. So far I've been talking just about the test signal. But the test signal doesn't play itself, doesn't measure itself. You have to play it and you have to measure it with something. I'll get to this at the end, we made a website for M-Noise. It's freely available to anyone. You can download it, and along with the signal is a document with a procedure for how to use that. And I'm going to walk you through that procedure now and some of the motivation. So this slide is about the motivation. You don't have to scribble down these equations. You're not going to have to implement these later. What this is explaining is that we recommend that you measure the frequency response with a transfer function, that you have an analyzer that looks at the input to the speaker and the output of the speaker simultaneously. And in order to measure the transfer function, you need these things called the auto spectra and the cross spectra, and those things are also useful for calculating something called coherence. And this is a bit like our lunch today out on the plaza. If you have a tortilla and some meat and some cheese, you can make a taco out of it. Or if you have a tortilla and some meat and some cheese, you can make a burrito or an enchilada. Or any restaurant that has those ingredients can make those different things. And so likewise, any analyzer that can do the Fourier transform and calculate a transfer function can also measure coherence. And so I'm going to talk a little bit about the benefit of using coherence and what it shows you. So we did a little example measurement in our studio in Berkeley. We have done the speakers with the blue horns. You'll see videos of that on the M-Noise website. What I'm about to show you is actually there's some speakers that are tucked just behind the console, and they're on stands that lift up. And so I'll show you an example of measuring one of these speakers. And first I want to talk a little bit more about coherence. There are three things that reduce coherence. So one is uncorrelated noise. So if there's HVAC, if there's a loud projector, if there's a truck driving by on the street outside, that signal is not at the input of your speaker, and it shows up, but it shows up at your microphone, and your analyzer sees that, and the coherence can figure out, oh, that's not in the input to the, this is a fun thing that I do at demos. When I do a demo of this, I'll walk over, play some noise to the speaker, walk over to the microphone and talk over there. My voice is not in the input to the speaker, and the coherence just collapses because there's this extra signal there that's not at the input of the speaker. Coherence can tell you that. There's also reverberation. So if there are reflections that are outside of the analysis time, that will reduce coherence. I'm not going to talk about that too much, but you'll see it happen. And then there's distortion, and distortion is what we're really after. And so if you can, and it's possible to place your microphone in such a way that the only thing that will reduce your coherence is distortion. So that's what this little demonstration is about. So here we are. Our microphone for the analyzer is at our normal listening position, and we see some ripple in the frequency response caused by reflections. And also the red trace there is coherence, so these big notches in the coherence because of these extra reflections. But as you move closer, your frequency response gets less ripple, and you have less of these holes in your coherence. So let's see what happens when we take it even closer. So when you get closer, it's possible to get even higher coherence, but you won't necessarily get the same frequency response that you get at the listening position. But it is possible to move around. When your microphone is, the distance is comparable, as the distance to each driver's, might be different, then you won't see a frequency response that's exactly like what you see at the listening position. But it is possible to move it around and get a frequency response that is pretty much like the one that you're getting at the listening position. And the rest of the procedure, which I'm about to show you, is sort of agnostic about the frequency response. You just need to see the whole bandwidth of the speaker. You need to see all the frequencies the speaker is producing. And then what we're looking for is a change. If you turn up the signal, does that response stay the same or does it change? So here we go. We're going to move our very closed microphone up a little bit, and we'll see that we can get a response that is relatively similar to what we hope the response is in the far field. Now, we recognize that that's not where you're going to listen. This not necessarily, you don't necessarily want to know what the SPL is. And if we could advance one more frame in this video, then we would see a little SPL meter appearing there at the listener position. So that's our recommendation, is you have a sound level meter at the distance where you want to know the sound level, and then you have a different microphone connected to a transfer function analyzer that records, that can have high coherence, that can see when the speaker is going nonlinear. So let me talk about nonlinearity. There are two different criteria for nonlinearity. One is that the output should be proportional to the input. So if your input goes up 3 dB, then your output should also go up 3 dB. And the other criteria is that if you play a signal through a linear system, and you play a second signal through a linear system, and you add those two outputs together, then you should get the same answer as if you had summed those two signals together and played them at the input. Again, you don't have to scribble these down or implement them. I'm just trying to show some of the motivation for what we're about to do. So you can take this idea of proportionality and you can divide the output and the input, and that says basically what I said before, is that if you turn the input up 3 dB, then the output should also go up 3 dB. And that's the beginning of our procedure. The beginning of our procedure is you take a guess of what's a signal level that the speaker can reproduce. And you measure that and you store it, and then you turn it up 3 dB and you see if it's the same. And if it's the same, then you were right, and the speaker is reproducing that linearly, and then you can proceed to turn it up even more until it shows some nonlinear behavior. So that's what we're going to show here. So this is our preliminary playback level. We took our guess, and now we'll turn it up 3 dB, and we see we can just eyeball it. Oh, that curve doesn't look any different. And now we're going to take that stored response, and we're going to offset it down 2 dB. That's our criteria for linearity. So that red curve there, that's our criteria. We don't want it to change any more than that. So we're going to continue to increase our playback level until the frequency response changes by that amount. And once it has, then we're going to let that play for a while. We don't want the speaker to get to the maximum and then die and never work again. You want it to actually be able to keep functioning. So we play it for some amount of time that you're concerned about, and then you record, okay, this is the SPL that it was at the onset of nonlinearity. So then there was this other criteria for nonlinearity, that summing the outputs of a system should be the same as summing the inputs to the system. So the way to think about that is to think of a single sine wave. If you play a single sine wave into a system, then the same sine wave and only that sine wave should be at the output. And if you play a second different frequency into the speaker, then there shouldn't be any intermodulation or harmonics of either of those signals. And that is what the coherence shows you. So here's a measurement of a speaker which is exhibiting some compression. So you can see the black curve there is is in between the blue and the red curve, but this speaker could still get louder. So you could increase the input of the speaker and the output of the speaker would still get louder. However, you have already seen a significant reduction in the coherence. So there is some clipping, distortion, or some other artifact going on. There is signal at the microphone, which is not caused by the input to the speaker. And that is nonlinearity, and that's something that we want to watch out for, and it's one of the reasons for putting this microphone so close is to be able to see the effect of distortion on coherence without the effects of background noise and other sources of coherence reduction. So we have a completely separate web page for M-Noise. It's m-noise.org. It's freely available for individuals. You can download it for free, use it in any way that you want, and it comes with that procedure that we recommend, which works with more than one manufacturers of analyzer, and we hope that you find it useful. So thank you.
Okay, opening the floor for questions.
You mentioned transfer function with the speaker. Does that also include the amplifier driving the speaker in the chain, or are you just looking at the terminals of the loudspeaker and its acoustic response?
You can do it either way. You might have to wire it a special way to make sure that your amplifier isn't dumping power into your analyzer. But it is possible to do that. However, the more of the system you include, I think, the better. So if your amplifier is clipping, and honestly, the thing to watch out for is very often when you're bi-amped, the amplifier running your high driver might have been undersized. Somebody might have thought, oh, the RMS level at high frequencies is lower. I don't need to have a big amplifier on my high driver. And you will discover, oh, when you use a signal that has a realistic crest factor, that actually you will need to reproduce some peaks at high frequencies. And if your amplifier clips those off, then this process will show it to you. So you want to have your analyzer reference before the amplifier if you want to see that.
Okay, additional question? Great.
Hi, I'm just curious how you were sure that your microphone wasn't causing the nonlinearity, and is it easy to find out, what kind of SPL the microphone should be able to take without being nonlinear?
Measurement microphone companies do usually specify that, and we've used that same microphone on speakers that go much louder than that. So we know that that particular one is good. I've never seen a microphone that had a linearity spec be wrong. So
in
I
terms
would
of
say
using the
look
method,
the
it's
spec
fairly easy to find a microphone that should be able to handle the high signal.
Yeah, the microphones that you would typically use for measuring speakers. It's not that hard to find a microphone that'll handle that level.
Thank you.
Okay.
They're often not. Those microphones often have a relatively high noise floor, so they're not the microphones that we would typically use for recording. But they are microphones that are very frequently used for measuring loudspeakers, and I haven't encountered one yet that was wrong about its linearity.
Okay, thank you. Excellent.